Hello, this is Sharon from the IB Wizards, and today we will be continuing our tutorial on data analysis. Specifically, we're going to be adding on to the file that Amir worked on in the last episode. So I highly suggest that you just take a look at that video if you want a little bit of contextual knowledge on what has happened already so that you can be up to date with what we're going to be doing today. Today we're going to be covering best fit lines, specifically equation labels, and the meanings of the numbers within your labels, the R-squared value, and then in analytics, the slope uncertainty and percent error, specifically how to calculate both of these and really how to tie these values into your conclusion. Now we can take a look at the graph that Amir developed in the previous episode, and there are just going to be a couple things that we're going to work on right here, formatting wise, to make this a little easier for us. And that's really two main things. One, it's the size of these labels right here. Excuse me. So temperature, volume, and then the title. And we're also going to work on reducing all this blank space right here. We're going to start this by changing the minimum value at which this label axis starts. And we're going to have this start at around 170. And we'll also do the same for the y-axis. So we'll start this at 250. Wonderful. Already, our graph is looking a lot more clear and a lot more visually appealing. This is really important for your teachers. You don't want to strain them when they're grading your lab. So please make your graphs very clear, but at the same time concise. All right. So again, we're going to increase the size of this font. And then do the same right here to the title. Now to pull up your equation label, you're going to click on your desired trend line, go to Format Trend Line, and then Display Equation on Chart, and also the R-squared value. You only have to have your R-squared value for your base trend line, your best fit line. And let's color code this appropriately, and then increase the font size. There we go. All right, let's talk about what these numbers really mean. Y equals approximately 1.5 plus approximately 1.4. So right here, we know that our m value, right here, 1.5, is the rate at which this equation changes. We know that for every Kelvin, so for every unit of Kelvin, every 1 unit of Kelvin, the volume increases by approximately 1.5 milliliters. That is the relationship that our best trend line is trying to fit onto our data points. And then right here, our b value, so our slope, our y-intercept. What does this really mean? Why do we have this number here? Well, if you've taken a little bit of thermophysics, you'll come to know that this line really, this value right here is sort of not supposed to be there. This graph is supposed to run through the origin to an extent or come very close to the origin. It shouldn't really have this intercept right here. But why? Why do we have this intercept? Well, in the real world, when you're conducting an experiment or really taking measurements of any kind, you are going to run into various uncertainties, some of which you can control and reduce by improving the procedure of your lab, but many others you won't be able to. So oftentimes, this y-intercept value is representative of the uncertainty in your system. So it essentially offsets your data by a little. That is how you can explain this value. Now it is not completely comprised of your uncertainty in certain cases where you will have that b value as maybe some sort of constant perhaps in a different system. But for the most part, it's mainly going to be representative of your uncertainty in IB1. Your R-squared value right here essentially tells you to what extent your blue trend line fits your data points. So you want this value as close to 1 as possible, and right now it's 0.999, and that is extremely close, and it's about the closest it'll probably ever get, really, if I gotta be honest, unless your data points are perfect, which in most cases that does not happen. But this really tells you to what extent the equation up above can be used to make claims. If your R squared value is a lot lower, it's telling you that your best fit line isn't really fitting well with the data that you have collected. So your data may have been, inconsistent with the actual system that was supposed to occur. You might even be using the wrong type of trend line. That is also an option. For now, you are most likely going to be subjugated to these linear options, but later on, you might have to use exponential, logarithmic, polynomial, power, or moving average to fit your data points a little better based on the system that you're working in. Now, just because your R squared value is low doesn't mean you should be trying these different options that you have, but it is indicative of how well your data points fit that line. Understand that. All right, now slope uncertainty. How do we calculate that? Well, first we need to find the slopes of our max and min trend lines. And to do that, we're just going to repeat the same process that we did for our best fit line when we pulled up its equation. So we're going to double click, display equation, and then do the same. Again, let's color code these so that it's very clear which is which. And increase their size. Wonderful. Now to calculate our slope uncertainty, we're just going to take the m values of both of these equations, find the absolute difference, and then divide by 2. So we're going to go to slope uncertainty equals m sub 1 minus m sub 2 divided by 2. And because this is a absolute uncertainty, it's very important to have this in 1 sig fig. Absolute uncertainties can only be in 1 sig fig. Never forget that. So this right here is really the uncertainty on our m value and our best fit equation line. So this approximate 1.5 has a slope uncertainty of 0.08. And again, precision matching will cause you to have this only up to the same place as the slope uncertainty. So let's adjust that real quick. Because this is in the hundredths place, you can only have your m value right here in the hundredths place. And there we go. This is your slope, and this is your slope uncertainty. Now moving on, we need to understand percent error and how that really factors into your lab. So most likely in IB1, as of now, you will be solving for a specific value perhaps that you already know exists. Let's say gravity, for example. And perhaps you might even be working on a lab where you will calculate the value of gravity through these slopes. You might have to multiply your slope by a certain number. Who knows? But at the end of the day, what you're going to be doing is you are going to find the absolute difference between your theoretical and experimental values, and then you are going to divide by the theoretical value for whatever quantity you are trying to find the percent error on. So let's say that in this case, our slope right here is supposed to be 1.6. So we would do the difference of 1.6 and then our slope right here. And then we're going to divide by, 1.6. And multiply this by 100%. Now that you have your percent error, it's important to understand how you can use these two different numbers to work to your conclusion, to your claim that you will be making. A lot of the times, students will make the claim, this lab was, to a large extent, accurate in predicting the value of whatever it is that you were trying to predict. Let's say it was gravity. Who knows? You might be working with gravity in the future. But you might say that your lab was to a large extent, accurate in predicting the value of gravity. And you can really do that by using these two values right here. Based on your slope uncertainty, you can figure out the margin that your slope could have fallen into within your lab. And so, because you know that margin or that really range of values that you could have gotten, you will know if that falls within your percent error. So if your percent error falls within that margin really, then you're all good. So what I mean by that is 1.6. 1.6, let's say, is our theoretical value, and we have a 5% error on that. So that's really approximately 0.08, and that's pretty good. 0.08 is pretty good in this case. Having a 95% sort of accuracy, if you will, is fairly high for most of the labs that you will be working with in IB1, and that probably won't happen. But what it means is that you could have been you were essentially 5% away from the actual value. So you were 0.08. And at the same time, we see here that 0.08 is actually our slope uncertainty. So because both of these values are so close to each other, we know that your lab, to an extent, did indeed predict the value accurately. It was just that all the uncertainty within the lab was prohibiting you from getting the actual value that you were supposed to. And this is really prevalent even more when we take a look at the max slope. So our max slope is around 1.6. And like I said, let's say that the theoretical value for our slope is supposed to be 1.6. We know that if all of our uncertainty had culminated in a specific manner, specifically by adding, onto all of our data points, then it would have ended up being approximately 1.6. So we do know that indeed, yes, our lab did accurately predict the value that we were supposed to be finding. Thank you for watching. Have a nice day. See you later.